Hi friends, today we are going to study about electrical circuits, and in this video we are going to learn about some basic fundamentals like why electrical circuits is required and some fundamental properties, the difference between source and load, and what is circuit and a network and what is the difference between them, and then parts of a circuit and some general definitions, Kirchhoff's voltage and current laws, and star to delta and delta to star conversions. So now, why do we need electrical circuits? The entire electrical engineering can be understood through two concepts. One is fields and one is circuits. We will now talk only about circuits. And in circuits, what is the need of circuits? Actually, through circuits, the entire complex power system, ours is an entirely complex power system. So entire complex power system can be understood through simple mathematical equations. I mean, it is a simple maths. I mean, our power system consists of a lot of different topics. I mean, basically our power system is to transfer power from a generating station to a load center and it will involve a lot of complex process. So now we'll know about some fundamental properties. And if we consider any electrical material, it has three properties. One is resistance, one is inductance, and one is capacitance. And all these three properties are distributed throughout the material. We cannot actually separate them individually. We will just do this for mathematical purposes. And now when coming to the resistance, actually when the current flows through the electrical material, it will dissipate some heat. And through this heat, some amount of energy is lost. So this property of substance is generally what is called resistance. And when it comes to inductance, the same. When the current is passing through the material, whenever a current passes through the material, some magnetic flux exists around the conductor. This property of the material comes under inductance. When it comes to capacitance, when two conductors are energized, I mean, if these two conductors are energized and there is separation between these two conductors, and then there will be a capacitance will be formed between these two conductors. This property of this electrical material is called capacitance. So now we'll know about resistor. This is how a resistor is actually drawn, and whenever a current passes through the resistor I, and then this is the voltage across the resistor V, and the VA relationship in a resistor is given by V is equal to IR. We'll later study about this. This will come under Ohm's law, and we'll study about Ohm's law later. And when it comes to the physical expression of resistance is like this. If you consider a conductor, let the length of the conductor be L and the area of cross section of the conductor be A, then the resistance of that piece of conductor can be given by R equal to rho L by A, where L is the length of the conductor it can be in centimeters or meters, and where A is the area of cross section, and this can be in same centimeter square or meter square. And when it comes to rho is the resistivity of the material. Actually, resistivity of a material varies. It is not fixed. It depends upon the type of material we use to manufacture the resistance. The units of resistance are ohms, and it's denoted by the symbol, this symbol. Now coming to the materials which are used for the manufacturing of resistance, we use tungsten, carbon, nichrome and ceramics, and the reason for using these materials is they have high melting and boiling points. So whenever we manufacture resistor from using these materials, actually they have high melting and boiling point. So even if a heat is generated, whenever a heat is generated, they generally do not get affected because they have high melting and boiling points. And now we'll talk about the temperature dependence of resistance. Resistance does depend on temperature. Actually, whenever there is a variation in temperature, then the resistance also varies, and this variation is given by the formula, R equal to R0 into 1 plus alpha T. where R0 is the initial resistance. Actually, we'll calculate the resistance of a substance at a particular temperature. Let it be T0, and let the resistance at this particular temperature be R0. And if there is a variation in temperature, let us say this temperature varies to some T. So then the resistance will vary according this. Will follow this equation. Actually, it will vary like R equal to R0 into 1 plus alpha T, where R0 is the initial resistance and T is the temperature in degrees centigrade, and where alpha is the temperature coefficient of resistance. And we can classify these resistors into the resistance can be either positive temperature coefficient or negative temperature coefficient. If the parameter alpha is positive, then it will come under positive temperature coefficient material, and if alpha is negative, then it will come under the negative coefficient material. And when it comes to the applications of resistance, where the resistance is actually used, it is used in heaters, incandescent lamps, and iron boxes. All these applications actually they involve a lot of heat. They utilize heat and then they work. So resistance is generally used in these type of applications where there is where we want a lot of heat. And now we'll talk about inductor. And inductor is nothing but basically a conductor which is not in a straight way, but it is wound. And it is wound around a particular core. So whenever we wound a conductor around a material, then it will give rise to inductor. An inductor will have turns and it will have a core material which will be most probably a good permeability core. So that the magnetic flux can easily pass through that core. That's it. So now when we come to the basic formula of inductance, it is like this: L equal to mu n square A by L, where mu is the permeability. Mu is also given by mu naught mu r, where mu naught is the permeability of air, and mu r is the relative permeability. So this is the VA relationship of an inductor. V is equal to L di by dt. This also comes under Ohm's law, and this will also we'll study later. And the units of inductance are volt second per ampere. As you can see that L is nothing but, you can shift this time units here and this current units down, then we'll get the volt second per ampere, or it's simply the units of inductance is Henry. Now coming to the application of inductors. Inductors are used in transformer and machine windings, and then they are used in electromagnets. We all know that electromagnet means whenever we wind an electrical conductor around a ferromagnetic substance, and whenever we pass the current through that wire, then the ferromagnetic substance around which the conductor is wound generally turns into a magnet. That is nothing but electromagnet. And then filters. Filters are generally used to generally reduce the harmonics, and chokes are used for starting the abscess of tube. Now coming to capacitor. Capacitor is nothing but whenever two conducting plates are separated by a distance d, and between these plates, and if a dielectric is placed, it may be either a dielectric or an insulation, then these two parallel plates form a capacitor. And the basic formula for a capacitor is C is equal to epsilon A by D, and epsilon is nothing but permittivity, and epsilon is given by epsilon naught epsilon r, where the value of epsilon naught is 8.854 into 10 power minus 12 farad per meter. It is a constant value, and epsilon r is a relative permittivity. And then coming to the VA relationship of an inductor, it is given by I equal to C dV by dt. This is also can be explained using Ohm's law. And then the units of capacitance is ampere second per volt. Just switch these things, switch this time unit here and this voltage unit down, then you will get ampere second per volt, or simply farads. Now coming to the practical applications of a capacitor, we can use capacitor in filters and then power factor correction devices. These are actually used in power systems, in practical power systems where we need to maintain a very good power factor at the load side. And then we can also use this in static wire compensators.